Welcome back, class. So in this recording, let's try to look at problems associated with section 7.2 that I covered in my last recording. So 7.2 was the basic gain cell in an integrated circuit, a form of the gain amplifiers, CS and CE amplifiers. So let's look at some problems and examples from the textbook. So starting with example 7.1 from the textbook, which is on page 498, and I'm on slide 7 of my PPT. It's a very basic example. Again, it's worked out in the textbook, so I expect you to go through it in detail. But basically, it's a very essential comparison of a CS amplifier versus a CE amplifier. CS with the NMOS transistor and CE with the BJT transistor. So because we always want to know about both and we are using a common methodology to understand amplifiers in general, this example gives you a good comparison. So certain process parameters are given for each of the two types of transistors. For NMOS, you have the L, W, the 0.25 process length is given, the Kn value is given, 267, also V prime A or VA prime, the early voltage is given. Similarly, for a CE amplifier with the BJT, you're given beta and VA, the early voltage. So based on all this, do a comparison, right? So I've tried to show you the formulas that have been used here. The main thing, obviously, the intrinsic gain is what is important. That formula applies to both, is GM RO. How to find GM for the MOS case is to the left. How to find GM for the BJT case is to the right. So these are the formulas used to go through and find various things. ID is given for both 100 microamps or the bias current, 100 microamps for ID, and here it's IC used in the formula. So go ahead, look through it. There's not much more I can tell you. I guess what you'll be surprised, not surprised to see that the gain, intrinsic gain for a CE amplifier is about 400, while that for a MOSFET is only about 30. So, that's what we are expecting, right? That the gain of a MOSFET amplifier is much lower, maybe 1/10 of the gain of a BJT type amplifier, which you can see proven in this example. Okay? All right, I will move on to slide number 10, which is an important and complicated set of examples. There's actually two examples, 7.2 and 7.3 on page 500. 7.2 is actually a nice description of the current mirror idea. Okay. Again, I will let you read most of it. It's not difficult to understand because the two PMOS transistors operate together with, their backs are tight to each other. You have to go through, and then of course Q1 and Q2 form another pair. So the analysis of this is shown. Some of this we'll repeat again next week, so I'll hold off until then. But I advise you to look through this and understand that when you have, this is almost like your inverter, right? Remember the basic CMOS inverter consists of a pull-up transistor and a pull-down transistor, the NMOS and the PMOS. This is similar to that. We are deriving a transfer characteristic V input to V output. You've seen this before, this curve. So a slight difference in some of the terminology, but basically the theory is the same of how to create this transfer function. So I'll let you read it, and then there's a numerical example based on the ideas shown in 7.2, where a lot of process data is given, and we are asked to solve for small signal voltage gain. Small signal voltage gain, and also these two important points A and B, which define the linear range. I'm trying to look here. Okay, small signal voltage gain is 42 volts over volts for here. So some of the important things that I can at least mention to you is that the I reference here is also the currents ID1 and ID3, actually also ID2, but ID3 is here anyway, but that is also the current in this drain, which is also the current in this drain, right? So this one I reference appears everywhere. That's one thing to remember. Also, these two are a matched set of PMOS, so the overdrive voltages will be the same because the same current is flowing in their drains also. So because they are PMOS, we put the absolute value of VOV, right? VOV for 2 and VOV for transistor 3, and they are equal. So that's another fact that is shown. Here is a fact also that's interesting. GM, the formula for GM of Q1 is written in this way. And we know that this is because GM can be derived like this. The ID has this form, and so it can be put in this form. So he uses this form to come up with GM as 0.63. Then RO1, RO2 are also calculated, and then A is calculated. The gain is just the product of GM times RO1 in parallel with RO2, which is a formula which we saw here, right? So the same formula is used. I guess I can copy that and add that here too as a formula being used. Okay. Lastly, here's a pair of important points, A and B. A and B define the linear portion of the transfer function of the input-output curve that we use for amplification. And so at this point B, which is the lower limit, that point, the voltage on the output or the input, right, Vi here, those can be derived from this graph, right? So the point B is nothing but VOV1. So the overvoltage of Q1 is this lower limit, and the upper limit, A, the voltage, the corresponding output voltage there called VOA, is nothing but VDD minus the overvoltage of Q2. So these two formulas are also useful and important, and using all these formulas he solves for 7.3. Okay, so you can see the gain was derived to be about minus 42, and then he finds points A and B which define the output voltage swing, right? And so VOA is 0.32. Sorry, VOA is 2.45 and VOB is 0.32. So the swing on the output side is 0.32 to 2.45, and you can also derive the swing on the input side. That means here VI, delta I VI is 0.045, which he also derives in the back of the example. So look through it, it's pretty interesting. I think where it gets complicated is the second part, where he starts taking the early effect into account. I mean, even without the early effect, you get reasonable good answers, but with the early effect, you get more precise answers. So instead of 2.45 for VOA, you get 2.47, which is a slight difference. And so, is it important? I don't know. It's there. I'm not going to ever ask you to include such complex calculations, but at least if you learn the top half of the solution, I'll be happy. Okay? All right. So that is another pair of worked examples, 7.2 and 7.3. We have one such example from the back also of the chapter that I will do for you, and that should help you understand that current mirror business a little better. Okay. All right. So let's look at another simple example first, which is problem 7.5. So I've got a bunch of problems in the back in a row, so I will go through each one of them starting from slide 13, one after the other. So 7.5 is an example of a NMOS transistor gain cell fabricated with 0.18 micrometer technology, for which we are given these values, this and this. VA prime is given and KN prime is given. It is required to obtain an intrinsic gain of 20. That means AO has to be 20 and a GM of 2. Okay. More data is your overdrive voltage is given to be 0.2. With that, find the required values of L, WIL, and the bias current I. So, not a big problem, I mean, not a complicated problem, but you need to do problems like this to get practice with the numbers. In fact, I list this caution at the bottom. This L in this formula, it's given in micro, but you don't have to convert it, just directly put it as, as the given value. The L is 0.18, right? Just use it directly. These are the formulas to apply. I like to summarize the formulas at the bottom, so you know when you start doing the problem how to proceed. So AO is like this, GM is this, ID you need, which is dependent on the overdrive voltage, which is given, and everything else is given, so you can easily find ID. Once you find ID, you can find GM, then you can find AO. All right, so let's look at that first. So Kn is given, Kn prime is given, Va prime is given, V over voltage is it 2 volts? 0.2. I make a mistake. Yeah, this is 0.2, by the way. I'm sorry. Yeah, I use 0.2 here carefully, but I missed it here. AO is required, AO is given. GM is also given. So from this, we find L as 0.4 micrometers, right? Now remember, this process technology is also a length, 0.18, but that is not what we always use, right? In discrete transistor analysis, we use that value as it is. But in IC, we still have to calculate L, and sometimes you can't use the exact L, which I'll explain in a bit. But for now, we come up with a value of L as 0.4 because that's what's required, right? Find the required values of L, WIL, and the bias current I. So L is like this. Now GM gives us ID, right? I as 0.2 milliamps. So knowing ID, knowing everything else, we can find WIL from this formula as 25. Okay, so we only need W by L, yeah, not W itself. Okay. All right, so that was example or problem 7.5. Let's move on to problem 7.7. Problem 7.7, similar as the previous problem in that it is using 0.18 micrometer process technology, and we have to get some data from a table on page 554. Okay. Now this device has a channel L twice the minimum. Okay. So what that means is this 0.18 micrometer is the minimum process length. But our device is using L twice this. Okay. So that is how these problems are framed. You will find that either it's given as some twice or thrice as an integer value, or we are asked to find what should be the length B in terms of that integer applied to the basic process length. So in this case it's given, and other values given are the overdrive voltage and even the bias current ID. So given all this information, find GM, RO and AO, the intrinsic gain. This should be AO, by the way. Okay, the intrinsic gain. If ID is now increased to 100 microamps, so first he says 10 microamps, then he says ID is increased to 100. Then what happens to all these values? So that's an interesting thing. Then in part C, he says we have this overdrive voltage of 0.25, but ID is not 10 anymore, it's 100. Okay. Here also in part B we increased ID to 100, but the corresponding VOV changed, right? We were allowed to change it. Here the width itself is changing, right? So the width is changed to again keep VOV as 0.25 but at a higher ID. Then what happens to all these GM, RO and A0? So that's the interesting, there's actually other parts to this problem which I thought was adding more confusion. So let's at least look at these three parts A, B, C. Okay. All right. So the formulas to use are pretty straightforward. The ones I hope by now you become comfortable with these. The formula for ID, the formula for A0, GM, RO, which is in terms of VA and in terms of VA prime and L. Okay. So how do you solve this problem? 7.7. So process length is given to be 0.18 micro. VOV is given. ID is given. From the table for this process, and this table is on page 554, that's where I went and got it. For this process technology, VA prime is 5 volts per micrometer. Now also length is given to be twice the minimum, right? So L you should take as 0.36. And you use this L in these formulas. Remember, not to use the process length, but to use the actual length. So GM can be calculated like this as 80 microamps per volt. Remember that, it's micro. Similarly, RO is this formula, and that comes out to be 0.18 mega ohms. Sorry, the ohms disappeared, but this comes out to be 0.18 meg for the output resistance. So intrinsic gain GM into RO, 80 into 0.18 gives you the micro and the mega cancel, so you get 14.4 volts per volt. Pretty low number, right, for the gain. Now, if ID goes from 10 micro to 100 micro, that is multiplied by 10 times, what happens? The VOV increases by root 10, right? Not by 10, but by root 10. Why? Because of the square formula here, right? ID and VOV are related with a square. So if ID went up 10, this only needs to go up by root 10, right? That's why we say VOV increases by root 10. Similarly, GM increases by root 10 because GM and VO are directly connected, right? Because of this. Well, ID went up by 10, VOB went up by root 3. So GM increases by the division of the two, which is root 3 again. The roots, see how the square root of this multiplier comes into the picture. RO just decreases by 10, right? Whatever is 10, that decreases because RO is like this. And so it becomes 0.018 megohms. So thus the intrinsic gain, which is the product of this and this, now becomes even lower. It used to be 14.4, it's actually dropped to 4.55. So just because you increase the drain current or the bias current 10 times, the gain is actually dropped. So that's something interesting, right? Last portion or last section 3 of C, here we are changing W, right? In the W by L business, W is changed, is allowed to be changed. We don't know how much, but we know something is changed. But we are told now we consider VOV is 0.25 and ID is 100. So with this combination, then what happens to A0? It goes back to 14.4, which is what we had here. So I don't know what to say about all this data. There's some pattern here, right? If you are able to mess with W and increase ID but keep VOV the same, then you get the original 14.4 back. But if you, that was the original value anyway. So what is the lesson to be learned here? I'm not sure. We got the same values for AO with 10 microamp ID as with 100 microamp ID. And then if we increase the ID, we actually drop gain. So those are some interesting facts that I thought were there for this CMOS technology. And maybe we'll learn more as we go further in this course. So let's go to, yeah, this is where I picked up that piece of information. So for 0.18 NMOS, your VA prime is 5, right? So that's what is this table 7.8.1 on page 554. I've talked about this section, the appendix 7.8 previously. Again, I advise you, lots of great information here. I've never seen any other textbook show so much in one place. So become familiar with this, and this will be very helpful to you later. All right. We'll move to the next problem, 719, and then we have 720. So I only have two more problems to work with you. This problem, 719, hold on, and 720 are both related to the current mirror business. Okay. Here, though, as you may have already quickly found, we are using BJTs. Okay. So here, Q1 is a PNP transistor. That is the CE amplifier. Interesting, right? So far we have always thought NPN transistors are the gain cells. But here, transistor Q1 is operating as the CE amplifier, and it has an active load or a biasing current source load consisting of Q2 and Q3. Q2, the current mirror, right? Q2 is connected to Q1 as the load, and Q3 helps to create the reference current, right? We've seen this for MOSFETs a little more detail, but we didn't discuss too much about the BJT version. So I thought, let's do this problem and learn a little more about the BJT version, right? And the formulas and the problems. So note that the biasing arrangement of Q1, it's not shown. I mean, we have shown this VCC, but that's it. We don't see much on the base side of the PNP transistor. So now we know that there is a current mirror in BJT form. What do we need to learn? Neglecting the finite base currents of Q2 and Q3, so there is not, it's not zero, right? For FETs, MOSFETs, the gate current is always zero, but for BJTs, the base current is not zero. There is a small value. But neglecting that, and assume that the VBE voltage drop, which is a diode drop, right, base to emitter in both cases, is 0.7, and that Q2 has 5 times the area of Q3. I think I missed that, but I should probably write Q3. Find the value of I. So this is what we need to find. Okay. Now I is the I reference, which is also IC3, and you get this I. Well, first of all, I reference is IC3, right? It's in the collector of this Q3 circuit. But this I is not equal to this. It depends on the proportion of this area business, right? We are told that Q2 has 5 times the area of Q3. Hence, we use this relationship that the collector current here in transistor 2, which is also the reference current we use for this whole business, that is area times IC3. Okay, so this is an important relationship. We may have studied it in the past, but definitely it's important to know this here. Then another important thing to notice is the total output resistance, which is what is expected here in part B. Q1 and Q2, we are given the early voltage as 30 volts. Find RO1 and RO2 here and here, which is what this output voltage C is looking inside, the parallel combination of RO1 and RO2, and he calls that the total resistance at the collector of Q1. So this is the collector of Q1, right, where the output voltage is taken. So what is the total resistance? That is the parallel combination of RO1 and RO2. Now you know how to find RO1, RO2. It's something like this. So GM1, this formula, R pi, the input resistance of 1 is given by beta by GM. Then for the whole amplifier, our input is R pi 1, our output is nothing but R total, this RO1 parallel RO2, and the overall gain, not the intrinsic gain, but the overall gain of the amplifier is minus GM1 into RO. Okay. So this is to answer C and D. All right. So let's look at 790. I reference is IC3, which you can find from the collector circuit, right? 3 minus uh, 3 minus the VBE3, which is just the diode voltage 0.7 divided by the resistance in the collector circuit, gives you the I reference. Now IC2, as I said, which is the actual I, the constant current I, for a BJT, you have to look at the ratio of the areas, and so 5 times IC3, which is 0.25 milliamps. Okay, 5 times this. Now RO1 is V by I, 30 by 0.25, 120K. RO2 also is the same, 120K, because they're all matched, right? VA is the same for both Q1 and Q2. So our total is 120 in parallel with 120, which is 60. GM1, simple, IC1 by VT. We found IC1, which is I, which is IC3 also, as 0.25 milliamps divided by 0.025 volts, which gives you 10 milliamps per volt. R pi 1, the input resistance, is beta by GM1, comes out to be 5 kilo ohms. Rin is this, RO is this, AV is this. So the three important amplifier parameters, input resistance, output resistance, overall voltage gain, is simple formulas are applied, and you can get the voltage gain as, it should be a minus sign, sorry, missed it. Is it a minus sign? Yeah, it should be a minus sign. So let me fix that. Okay, all right. So that takes care of that problem 7.19. Okay, so this is like a current mirror, but with BJTs, and the current mirror is formed by NPN transistors, while the amplifying transistor is a PNP transistor, right? So all we needed to find simple things here, basically the current I, find the value of I, this I, and these process amplifier parameters, input voltage, output voltage, and gain, right? The next problem on CMOS current mirror is a little more complicated, because here we are asked to find this voltage swing and all that. So we haven't studied for this previous BJT case, for this case, we haven't studied the input-output transfer characteristic like this, right? Maybe we'll study it again later, but for now, much of this kind of analysis and the voltage swing, etc., the signal, how much signal can be provided on the input so that the transistors don't go into, cutoff region, triode region. That kind of analysis we have only studied for MOS. So let's get to it and do the CMOS amplifier problem 7.2. This is quite similar to what we already saw in the example, so the steps will be similar. But since it's an important topic, I thought extra practice would be helpful. So again, it's a 0.18 micrometer process. VDD is given to be 1.8 volts. All these other parameters are given: Kn prime, Kp prime, Vtn, Vtp, V prime A, the early voltage, are different for N and P. Sometimes they are given to be the same, but in this case, they're different. Also notice that this is given with a negative sign, right? Now, we start to look at amplifier behavior here. The output voltage must be able to swing to within approximately 0.2 volts of the power supply rail. So the power supply rail is at 1.8, right? 1.8 and 0. So we need to go 0.2. That means on the low side, we have to be able to go as low as 0.2 here. And on the high side, we need to be able to go as high as 1.6. So these 2 points, VOB and VOA, are given. And the voltage gain must be at least 10 volts. So given that, we are asked to design for a DC bias current of 50 microamps. So this I will be equal to the I reference in this case is 50. And use devices with the same channel length, right? So L, keep it the same. Find OV1 and OV2 basically. When they say design, that's what it means. We are given VOA, VOB, what it should be. So find OV1 and OV2 in this and this. If the channel length is to be an integer multiple of the minimum 0.18, so we are given this, so integer multiple, what channel length is needed and what W by L ratios are required. If it is required to raise the gain by a factor of 2, so here it is 10, if you want to make it 20, then what channel length would be required? By what factor does the total gate area of the circuit increase? That means the areas of all these three. To get a gain of 2 or twice this 10, how much increase in area has to be accomplished? How much more silicon are you going to use? That has to be calculated. So lots of interesting stuff here. The formulas are, again, many of these are, by now you should be familiar. ID, W by L based on this. For 2 and 3 it's the same, right? Because they are a matched PNP set. I reference is ID2, ID3, ID1. So for a CMOS case, this I reference is all the same drain currents. For PMOS saturation, VSD has to be greater than absolute value of VOV. I just thought I'd throw this in somewhere because it's PMOS saturation. These have to be saturated. Then these two important formulas that help us set this maximum swing of the output voltage, the V output here. From there you can derive the VOV1 and VOV2, which is part of the answer here. Finally, we also need this information, these formulas, to find W by L ratios. Okay. All right, so let's see how to solve this. Assignment 20. So VOA, VOB is given, output 1.6 for the PMOS. This formula, right, source to drain for 2, right? For 2, the source to drain voltage is what we need to find. To keep that transistor in saturation, this source to drain voltage has to be VOV for that transistor, right? So, and we know these formulas also, right? This formula. So 1.8 minus 1.6 gives you 0.2. This is the VOV for that PMOS transistor. The other rule for the output, the low output, 0.2 volts, we know that this is directly VO1, VOV1, right? Because this is the VDS1 minimum. So that is the importance of understanding these two formulas, right? Okay. So that's answer to section A or part A. Part B, I reference. All these currents are basically the same thing, which is 50 micro or 0.05 milliamps. Then using this formula, we get W by L, which is required to be 29. For transistor 1, now remember 2 and 3 are PMOS. NMOS, the W by L is different. It's similar to that idea of, BJT, one transistor having bigger area than the other, something like that, even though they were both the same NPN transistors. Here they are different, NMOS and PMOS, but NMOS has a W by L of 6.46 while PMOS is 29, okay, using this formula. And we get these overdrive voltages from above, from here, which happen to both be the same anyway, 0.2 volts. So given that VAV must be at least minus 10, you plug that in, you come up with, and GM1 for transistor 1 you can directly calculate as 0.5. So you get a value for RO1, RO2 as 20K, right? Now RO1 is this, use this formula, which is this VAN prime is given as 5 and minus 6, right? These two values are given. So using that, you can write RO1 is 100L, RO2 is 120L. Make sure you understand this step. Then 100L in parallel with 120L we know is 20K as derived here by using another formula, from which you can solve for L and it comes out to be 0.367. So L must be an integer multiple of the process length 0.18. So we have to pick an L of 0.54, 3 times this. If you can pick 2 times, then it becomes 0.36. but that is less than what we need. So we are forced to go to 3 times, so we get 0.54. So that is the length we are going to use in this design. Then for part C, to raise the gain to 20, this parallel combination of resistances should double. So L will also double. L must be an integer multiple of 0.18. So you need to be 5 times this. So L now becomes 0.9. So all the L's increase by 5 by 3, right? They were previously 0.54. Now they are 0.9. So they've gone up by 5 by 3. W's also have to increase by 5 by 3 because W by L we need to keep constant. We are not allowed to mess with that, right? So with L and W increasing, the previous area has to increase, right? So previous area was this much. The area of Q1, the area of Q2, area of Q3, which is width into length. But we don't know width separately. So we use W by L into L square. We are given this. So you get 18.85. New area, using the same method, you get as 52.37 with the new W by L's. Well, the W by L is the same, but the new L's, right? L is 0.9 everywhere. Well, 0.9 for 2 of them, and the other one also increases by 5/3. So anyway, the new area is this. You can calculate using this. And the increase then is 2.78. So to double the gain, you need an area increase of almost 3 times. That is the lesson to be learned. Okay. With that, I end this chapter, well, end at least this week's material on chapter 7, and we'll continue next week.